Okay, the purpose of this video is to explain how the angular separation equation is derived. The angular separation equation is this one here, and it basically tells you what is the angular separation between two objects if you know the rate ascension and the declination. This formula is usually simplified under different circumstances. Like, for example, if both objects are in the same right ascension, then you can get the angular separation by the difference of declinations. And then with the same declination, the formula gets simplified further, but in general, under some generic circumstances, you can express the equation like this. So what we are going to do is we are going to derive this from scratch and then see how we get to this one, and finally this one. Okay, to start with, let's draw a coordinate system. So let's draw the three axes and let's label them as X, Y, and Z. And to determine a point on this coordinate system, we only need three coordinates, which we are gonna call X1, Y1, and Z1. So X1 will be in the direction of the x-axis, then Y1 in the direction of the y-axis, and Z1 in the direction of the z-axis. This will be the location. Now, this will be X1, is in the direction of the x-axis, then Y1 and Z1. But there is another way of determining this point, which is using degrees. And it's like if you look at the location of this point from the top, you could say that is alpha degrees clockwise from the y-axis and also beta degrees counterclockwise in the direction of towards the z-axis. So we got, actually let's call it alpha 1, beta 1. So we got two ways of expressing the location of this point. Okay, so now what we're gonna do is express x1, y1, and z1 as functions of the angles alpha 1 and beta 1. To do this, first, let's take a top view from this coordinate system, and the top view will be this where y is here and x is here. And then top view will be that the point is located where this is x1, this is y1, and then in green this angle alpha 1. In the same way, we can have a side view. Let me remove this. And the side view, actually, let's take a side view in the following way. So this line alpha, let's take a view like this. So let's try to make it simple. This, and then the vertical z-axis. So this is the z. Let's call this the h1 h-axis. So this point will be located, let's say, here. And it will be, well, actually, it will be at a high Z1, then at an angle beta 1, and then this distance, let's say, is h1, which will be this distance here. This distance is h1. Now, with all these three drawings, we have all the information that we need to... Oh, wait a second. That means this is beta 1, and this length, let's call it L. Cool. So if we want to express, for example, x as a function of alpha, then that will be this distance, and this is the hypotenuse, which is also h1. This will be from the top h1. So will be x1 is equal to the sine of alpha 1 times h1. So sine of this angle opposite over hypotenuse. Then with y1 is the same thing. Whoops. Y1 will be cosine of alpha 1 times h1, and then z1 over here on the right will be sine of beta 1 times L. Cool. So let's erase, actually let's make one more point before moving on, and is that this point A is located in the surface of a sphere of radius 1. So this sphere is centered about the center of the coordinate axis and is located at a distance 1 from the center. Like any point in the surface of the sphere is located at a distance 1, which means that L equals 1. Now, with all this data, actually, we only need one more thing to do, and is, let's say, what is h1? And h1 is the cosine of beta 1 times L. Cool. We have all the data that we need to express the point in rectangular coordinates as functions of the spherical coordinates. Actually, before doing the factorization, let's remove the definition of the points here to have more space. Okay, so this will be cosine of theta, will be cosine beta 1, cosine beta 2, and then is times sine alpha 1 sine alpha 2 plus cosine alpha 1 cosine alpha 2. This is all factorized multiplied by this, plus sine beta 1 times sine beta 2. Okay, cool. And now, finally, knowing that this is another way of writing cosine of alpha 1 minus alpha 2. And now we can simplify this in cosine theta equal cosine beta 1 cosine beta 2 times cosine alpha 1 minus alpha 2 plus sine beta 1 sine beta 2. And that is the whole formula. So as long as you have all the angles, you can express the location of the 2 points with angles, you can now find the separation between them. And this is actually the same equation that we saw at the beginning of the video. Cosine theta, sine delta 1, sine delta 2. In our case, we use beta instead of delta, but sine beta 1, sine beta 2. And then plus cosine delta 1 cosine delta 2 times cosine of alpha 1 minus alpha 2. And in this case, it is cosine alpha 1 minus alpha 2 times cosine beta 1 cosine beta 2. It's the same equation, and we have derived the angular separation. Okay, so now we are gonna put some special cases. The first one and the easiest is when alpha 1 is equal to alpha 2. So in that case, cosine of theta is equal to cosine beta 1 times cosine beta 2. This is cosine of 0, which is 1, and then plus beta 1 times sine beta 2. And this is exactly the cosine of beta 1 minus beta 2. So what we got is the cosine of theta is equal to the cosine of beta 1 minus beta 2, which is the same as saying that theta is equal to beta 1 minus beta 2, or effectively the difference of beta. Now we can see that in this case, when it's the same right ascension, what in this case is alpha 1 and alpha 2, we get the same, which is the difference of the two declination values. In our case, it's beta 1 and beta 2. Now, for the next scenario is the case where beta 1 is equal to beta 2. Actually, let me put it up here. Now we are going to assume beta 1 is equal to beta 2. So this means cosine of theta is equal to cosine of beta 1 squared times cosine of alpha 1 minus alpha 2 plus sine beta 1 squared. Cool. There's gonna be one assumption here, which is that the difference of alpha is really, really small. This in astronomy makes total sense, and that means we can expand this using Taylor series, and it can be replaced as 1 minus the difference of alpha squared over 2 sine beta 1 square plus sine beta 1 square. And if we expand this is cosine beta 1 square minus cosine beta 1 square this plus sine beta 1 square. And sine something square plus sine of something square is equal 1. So that means we can simplify this one and this one, place it for 1. So now we got cosine of theta is this. There is one more assumption that we can make, and is that if the angular separation is really small, we can express this as 1 minus theta squared over 2. Then it means that is 1 minus cosine beta 1 square difference of alpha square over 2, and then simplify 1 goes away, then the minuses go away, 2 goes away, and we are left with theta equal cosine of beta 1 times the difference of alphas. And if we check here, we can see how for the case of same declination, in our case declination is beta 1, then theta is equal to the difference of alphas times cosine of delta, in this case is beta 1. And now for the final formula, the assumptions are going to be that the difference between the angles is really small, and also the difference between the beta angles are really small. Of course, that the angular separation itself will be really small. Basically, when you're looking at stars, the difference between the right ascension and the declination will be very small, and the angular separation itself will be very small. So with that, we can use Taylor expansion to express everything in this way. So this is similar to what we did before. Sine beta 1, sine beta 2. Cool, and then we do this again. Expand cosine beta 2 minus cosine beta 1 cosine beta 2 plus sine beta 1 times sine beta 2. And it happens that this and this is equal to cosine beta 1 minus beta 2. So we can write all the same. This is of course equals to 1 minus theta squared over 2. Okay, and we mentioned previously that also the difference between betas is less than 1, so we can again use Taylor expansion for this. So that will be like this, minus cosine theta 1 cosine theta 2 and the difference of alphas over 2. 1 minus. Okay, so we can actually remove the parentheses. Now we can cancel the ones. We can multiply everything by minus 1, so that means this is a plus now. We can multiply everything by 2, so all the virtues go away. And we are left with beta square equal difference of beta square plus cosine beta 1 cosine beta 2 difference of alpha square. And it turns out that because the difference of betas is really, really small, this can be approximated as cosine of beta 1 square times the difference of alpha square, and we are left with the same equation as we have here at the end, theta square, the difference of the angles square times cosine square plus the difference of deltas square. Same. Okay. Now, if you're like me, the most surprising thing here really is that you can simplify this into this. And to explain it, I have this Desmos, which I made, where basically you have the original function without any simplification, which you can see here in green, and then the approximations where the only difference is here I use the here I don't change the cosines. Here I simplified as cosine of beta 1 square, here I do cosine of beta 2 square, and here I do the average. So you can see how when the difference in betas is really small and the difference of alphas is also really small, like here is center about 5.8, then every all the other approximations are quite accurate, extremely accurate. And I'm gonna leave these Desmos in the description so you can play around with it if you want, like modifying alpha, just shift the graph to the left or to the right. You can see how modifying, for example, this just makes the whole thing more or less accurate. Like for example, with zero point 0.2 difference is quite accurate. If we increase it like 0.9, it's less accurate, always accurate around the center, but here the difference is almost 1, while if we keep decreasing 5, 4, 3, 2, 1 is extremely, extremely accurate. So yeah, it's an easy way of simplifying the formula and make it very easy to remember.